So in this session, we like to put these creatures side by side. Covariance, variance, and correlation. We put them side by side because they sound the same. They are formula-wise connected to one another. For correlation is derived from covariance, and covariance sounds a lot like variance. And what's the co part doing here and all that? So let's put them side by side and compare and find out what's similar and what's different here. So for covariance, we are able to find the covariance of any two random variable. Remember, covariance is a descriptive. What is a descriptive? It's a single number summary of huge sets of data involving two measurements at the same time or on the same object. So x and y, like height and weight of the same person for many people, right? So covariance of height and weight is what we're talking about. So covariance can take will produce a number that represents a lot of pairs of measurements. Now these two measurements, height and weight, we can also say x and x, height and height, or weight and weight, because it's for any random variable. So we might as well just let y equals to x. We can do that. And when we do that, then that's covariance of x and x. And when we do that, that exactly produces the variance of x. So it is quite closely connected to variance of x, in the sense that if we let y equals to x, then we get back the variance of x. And of course, if we let x equals to y, then we have covariance of y comma y, then we get back the variance of y. What about the sample variance? Same thing. We use the sample covariance of x comma x, the same two variables. So what is the covariance of height with itself, of weight with itself? Well, that is basically the variance of itself, right? So that's how we get this connection between variance and covariance. Now, the correlation of x and y, if we let y equals to x, will be to ask what's the correlation of height with height. All right, so how is height correlated with itself? Well, when height changes, right? So it always instantaneously and faithfully will change at exactly the right amount all the time. So in other words, it's strongly positively correlated, perfectly correlated, right? So therefore, we should expect a perfect 1 here, and it is true because covariance of x and x is the variance of x. And downstairs, the standard deviation of x times the standard deviation of x is just the variance of x. So they cancel out, and no matter what x is, whether height or weight or stock price, mileage, it will always be 1. Likewise, for the sample correlation, what is the sample correlation of weight and weight itself? And the answer is 1 all the time. So it's kind of a trivial thing, but good to know that it's factually true. All right, that it's pointless to ask about the covariance of a random variable with itself because it's always 1. All right, so this means that x, whatever x means, can be stock price, height, or weight, is always linearly and completely correlated with itself. Now that's no big deal, right? That's no big science discovery. But then it's good to know it for a fact that yeah, your intuition is kind of mathematically, theoretically true, well supported, right? We don't take these conclusions for granted. We have to prove them, and yes, it is good in theory as well. Now, next thing is kind of both trivial, simple, but very important. And that is what happens when x, the random variable, is a constant, right? So what it means is if we let x equals to c, a constant. So what does that mean? So for example, if you measure a bunch of peoples and their heights are exactly 1.7 meters for all the sample heights that you take, all right, so it's a bit amazing, but it's not impossible to happen, right? So everyone is of exactly the same height to the precision of the measuring ruler that you use. So your x will be a repeated display of 1.7, 1.7 many, many times, right? So in that case, x is a constant. So we say x is a constant when we actually mean that the random variable holds the same value for all the measurements. So what happens then? What is the covariance of another variable that varies? Maybe they're all of the same height, but their weight varies. Yeah, so all these 1.7 meter tall people, their weights differ. Some are heavier, some are lighter. So what happens when we find the covariance of the height and the weight? Then the height is constant. So the variance of the height is zero because there's no variance, there's no change, right? The average is 1.7, and individual difference is zero. So the variance is zero. And that part we can understand. The interesting part is, let's know it for a fact that when we covary the weight which fluctuates with height which is not fluctuating, then the answer is zero. So there is no covariance whenever one of the variables is zero. So for example, if we have the height, let's say it follows bell curve, some sort of a bell curve, and the weight follows a bell curve, and the height follows a straight line, no change. Okay, so no change. Nope, sorry, straight line. No change means that all the heights are of exactly 1.7, right? So that's just a spike here, one bar here. All right. So what happens when we find the covariance between the two graphs? So the covariance of normal curve, let's say, comma a spiky distribution is zero. That's what it says. Is that okay? All right. So remember that x, the weight, can be population or sample. And if x happens to be sample, same effect happens. All right. So the covariance of a sample distribution, let's say normal distribution, with constant random variable is zero. So last property of covariance is that it's commutative. So it's a bit like multiplication. Remember we understood the motivation of covariance is as the average of all the areas induced by the data points, right, against the mean of x and mean of y. So the areas basically are length times height, and it's commutative, right? So we are kind of quite persuaded that covariance itself should be quite able to have this swapping capability. That means the answer should be the same whether we say covariance of x comma y or covariance of y comma x. There's no change in sign, nothing becomes negative, everything is exactly the same. So let's put it down as a fact that this is always true. Yeah, so this is true indeed.